Assalamualaikum warahmatullahi wabarakatuh and a very good day. I bid to both of Dr. Nazri and Dr. Wan. Today we are from Group 3 would like to present the final presentation regarding the RC plane project for subject Skma 4253 Aircraft Design 2. Before we started, let me, Naziha, explain a little bit about the outline for today's presentation. First, we are going to start with the brief introduction to the project and our RC plane. Secondly, we will talk about the propulsion system and performance before we go into the avionics and the control and stability. After that, we will start the structural analysis with wing, fuselage, landing gear, and empennage. And finally, we will talk about the flight testing and planning.
Hi, I am Wee. I will start my part with the introduction of this design. First of all, we are designing an UAV, which is a flying machine without pilot on board. The design criterion is maximum ground weight is not more than 5 kg and the maximum speed is not more than 20 meters per second. And then the maximum load factor is 3 and the minimum load factor is minus 1.5. And our aircraft must be able to carry 500 grams of payload. Next, the flowchart of our design. We started our design with selection of group members, then we distribute into 5 subgroups, and each group carry out feasibility study, determine the main aircraft specification, electronic component selection, aircraft CG component and stability, structural analysis, control system, and last but not least is flight planning and preparation. Next, I will talk about the cost estimation in our design. The total amount that we estimate in our design is not more than 500 ringgit Malaysia. We buy all the components almost online. First, battery, propeller, motor, ESCs, form, battery checker, receiver, and so on. All the total amount is 493 ringgit and 63 cents. Now let's see our 3D modeling of design. First of all, you can see we designed the landing gear with 2 landing gear on the front and 1 landing gear at the back side. And we decide to use rectangular wing and the top wing. Okay, this is the technical drawing and the side view of our aircraft, and front view and back view of our aircraft. And this is the top view, and this is the our front landing gear design, and this one is the back landing gear design.
Assalamualaikum, my name is Siti Masra binti Masko. So I will present about aircraft performance for our aircraft. So this is a list of components for our aircraft, which is motor, propeller, ESC, battery, servo and receiver. So the total weight for our electronic parts is 718.2 gram. So this is servo and receiver that we use for our aircraft. Firstly, motor selection. So since our aircraft need to operate with higher thrust and lower speed, so the range of electric motor that suitable for our aircraft is between kV 850 and kV 1500. So this is the motor that we choose for our aircraft, which is brushless motor SunSky X2116 kV 1100. So after choosing the motor, so we can obtain motor specification from the manufacturer. So from there we build power required versus velocity graph for our aircraft. So according to power required graph, the design speed of our aircraft is 19.3 meter per second. So in this case, we only refer the 2PR curve to obtain the design speed for our aircraft, since 2PR is more realistic than PR. So 2PR is referred to the value of doubling the power required. So in other words, PR is a very optimistic assumption where usually aircraft requires more than that. In steady level flight, the maximum velocity of the aircraft is determined by the high speed intersection of the thrust required and thrust available curves. So to ensure that the aircraft can function properly, thrust available must be always higher than the thrust required. So from the data we obtain from the manufacturer, we built TR and TA graph versus velocity. So from the intersection between TR and TA, we obtain maximum velocity for our aircraft, which is 21.5 meter per second, which is more than design velocity for our aircraft, which is 19.3 meter per second. So it can be concluded that the motor used in our aircraft can always provide enough thrust to the aircraft. So the second one is propeller selection. So after selecting the motor, the propeller that match with the motor is listed. So the table below shows the recommended propeller chosen for our aircraft, which is propeller Jumfan APC90545. So by referring information from the table, the estimated current used for takeoff, landing, and cruising can be obtained by using interpolation. So the table below shows the values. So the equation, the two equation that we use to calculate theoretical thrust is T gram equal to PD over C to the power of 2 over 3. So where C is the air density dependent coefficient at 30 degrees Celsius and at 1 atmospheric pressure. So the second equation that we use is efficiency, which is efficiency equal to thrust versus over theoretical thrust times 100. So this is the data for theoretical thrust and efficiency that we calculated. So the next one is battery selection. So the selection of battery is mainly related to the endurance of the aircraft. So the most important parameter is the battery capacity. Battery capacity shows the amount of current that's lost in the battery. So the C values indicate the discharge rate. So as you can see from the slide, where 35C, for example, 35C is a discharge rate for the battery, and the 1500 mAh is the battery capacity. So high C value enables the aircraft to have a short response time. So since the aircraft is designed to have a relatively low speed, the battery does not require a very high C value. So after consideration, the battery selected for our aircraft is TCB worth 5200 mAh for cell, 14.8 volt, 60C, 60 discharge rate, LiPo battery XT60. So this is the picture for our selected battery. After selecting the battery for our aircraft, we calculated endurance and range for the battery that was selected. So the endurance is 12.48 minutes and the range for the battery that was selected is 14,451.8 meter. So by referring to the flight consumption graph as shown in the slide, we can obtain the estimated time during flight, including takeoff and landing. From the graph, the time taken for our aircraft to take off, cruising, and landing can be obtained. So time for the takeoff is 0.35 minutes, time for cruising is 5 minutes, time for landing is 2.67 minutes. Therefore, the total time taken for our aircraft to fly is 8.02 minutes. So since endurance of the battery that we selected is more than the time taken for our aircraft, it is proof that the battery capacity that we choose is suitable for our flight test. So the last one is ESC selection. The maximum ampere of the ESC will be stated in the manufacturer data sheet. Based on manufacturer data for the selected motor, it is recommended to use ESC 30 ampere. But to make it safe, we choose Hobbywing Skywalker 40 ampere ESC because it is good to use an ESC rated at a higher amperage against overstressing the ESC, causing failure and potential damage to our aircraft. Then I will proceed to the performance calculation for our aircraft. So the Vstall that we obtained for our aircraft is 33.4058 feet per second. So the first parameter that we calculated is thrust required. So the equation that we use to calculate thrust required is stated as in the slide. So after we inserting all the parameters needed in the equation, we obtain thrust required for our aircraft is 17.5408. The next one, we calculated power available. The power available is related to the power generated by the motor. So the equation that we use to calculate power available is efficiency times the power equal to 146.359 watt, which is equal to 107.95 pound-feet per second. So the next one, we calculated power required for our aircraft by using equation thrust required times with V stall, and we obtain power required for our aircraft is 35.6774 pound-feet per second. And next one, we calculated rate of climb for our aircraft by using the equation stated in the slide. We obtain rate of climb for our aircraft is 9.9378 feet per second. And then we calculated takeoff performance by following the equation stated in the slide, and after inserting all the parameters needed in the equations, we obtain the takeoff performance, which is 20.84 meter. And the last one, we calculated landing performance by referring the equation stated in the slide, and after inserting all the parameters needed, we obtain landing performance for our aircraft, which is 65 meter.
Next, I will explaining about the VN diagram. The VN diagram provides a treasure trove of information regarding the flight performance for the pilots. It is a graph dissipating the variation of the load factor with the speed of the vehicle and understanding of what the load factor represents. It is crucial to understanding the VN diagram. Those who have watched the Top Gun or any of the military movies with fighter jets would probably have noticed the pilots calling out many of the G's they are pulling. They are in fact talking of the load factor of the airframe. Load factors provides a measure of the stress of the airframe is subjected to the and defined as the following equation, which will be the load we will discuss in the next slides. As we move on, load factor gives a lot of information on how it's going to work. If you look at one of the observation we make, it looks that parabolic curves is called the stall line and the branch out of the origin of the either side. Each curves represent a particular altitude. The graph gives us the stall speed and the never exceed speed and the limit load factors for a particular altitude. The stall speed for 1G flight is case is 200 knots up to the altitude. As we've done this example, from here we can see the load factor from the highest one will be at the 3 and the maximum speed will be at 18.5 meter per second. The airplane designers will construct the VN diagram using the multitude of the flight mechanics and structural stress data obtained from the simulation and tests. The crucial parameters is to determine the stall line in the lift coefficient, which is obtained in the CFD analysis of wind tunnel tests. Using the lift coefficient, one can calculate the load factor for the various speed and altitude. The crucial limits define the limit load factors and never exceed the speed. And for now, based on the graph we see, the flight envelope determines the aerial performance of the operating limits for the maximum speed and the load factors given a limited atmosphere density. The flight envelope is an area where the aircraft can operate safely. As we move on, will be the calculation for the VN diagram. All parameters needed can be obtained by using the following equations, such as the positive load factors and max. The positive load factors positive can be determined. The highest will be the 4.498. The maneuver speed will be the positive limit will be the 17.85 feet per second. The design dive speed will be VD 1.4 VC minute, where the VC minute is a cruising speed. Okay, the VD will be 88.6483 feet per second. Maximum negative load factor will be 0.4 times the negative maximum position. Positive will be 1.792. The maneuver speed is negative limit. As we can see, the highest will be the 50. The calculation, based on the calculation, we can get the 50.0978 feet per second. And for the curve part, the VN diagram, the curve is drawn by varying airspeed before maneuvering speed with equation. The n, the 0.5 rho v square SCL max over weight. For positive end region, the airspeed varies from 0 to 88.6483 feet per second. For negative VN, the airspeed varies from 0.50 to 0.0978 per second. That's all for me. Thank you.
Hi, I'm Adiseshan. Next, I will move on to the next chapter, which is the avionics and controls. I will start with the center of gravity of our RC aircraft. The center of gravity is the average location of the weight of the aircraft. The weight is actually distributed through the airplane, and for the maneuvering, we need to be concerned with only the total weight and also the location of the center of the gravity. The center of the gravity of an aircraft is the point over which the aircraft would balance. The center of gravity affects the stability of the aircraft. To ensure the aircraft is safe to fly, the center of gravity must fall within specified limits. There are four important center of gravity locations which are determined for the analysis of balancing and stability. The four important center of gravities are maximum weight CG, empty CG, aft CG, and also the forward CG, which will be shown in the following slides. The location of gravity of each components in our RC aircraft and the calculations of all the four center of gravities are shown. This slide here shows all the components of our RC aircraft and also their distance from the front of the aircraft, which is from the propeller of our aircraft. As you can see here, there are totally 15 components in our aircraft, and all of their center of gravity locations are shown in this figure. Next, I would move on to the maximum weight CG. The weight and location of each component are estimated, and then the multiplication of parameters are obtained as shown in the table below. After that, the maximum weight CG is calculated by dividing the sum of calculated values by the sum of weights of each components. It can be seen here from our calculation that the CG location in the horizontal axis of maximum CG is 0.4 meters from the front of our aircraft. In this slide, we can see the location of maximum CG on our aircraft. Next would be the empty weight CG. In this calculation, all the removable loads are removed, which in our case is only the payload. So the total items would be 14 by excluding only payload. From the calculation, we can see that CG location in horizontal axis is 0.39 meters from the front. It is shown in the slide here, the location of empty weight CG of our RC aircraft. Next would be the forward CG. In the calculation of forward CG, all the weights of components that are located, all the weights of removable loads that are located in front of our aircraft is included. The only removable load is the payload, which is located in the forward part of our aircraft. So it is located. So there will be 15 components in total, and the CG location in horizontal axis obtained is 0.4 meters, which is exactly same as our maximum weight CG. And it can be seen in the slide the location of our forward CG. Next would be the aft CG. In the calculation of aft CG, the payload is excluded from this calculation as it is located in the forward part of our RC aircraft. So the total components would be 14, and from the calculation, the CG location in horizontal axis is 0.39, which is same as the empty weight CG of our aircraft. And the location of the CG can be seen here in this slide. That is all for center of gravity calculation.
Protect Doctor and Tenjai. Now let us look into the longitudinal stability. This is important to ensure a stable aircraft is designed. First and foremost, the criteria of longitudinal static stability is investigated. First, alpha 0 is less than 0. Second, Cm0 is more than 0. The figure shows the moment coefficient curve of stable and unstable aircraft. For example, when there is a gust causes the aircraft to pitch more than the trim angle, the angle will pitch downwards automatically. Therefore, the aircraft will back to trim angle without pilot's control. The longitudinal static stability can be verified by using calculations. Firstly, the equation of slope of moment coefficient curve is introduced. This equation includes the effect of wing, body, and tail. Since the gross weight CG and forward CG are the same, the slope is calculated as follows. Same goes to empty weight CG and up CG. From the result of these two calculations, we can see that negative values are obtained, which means that it is a negative slope. This means that the first criteria is fulfilled. Secondly, the equation of moment coefficient at zero angle of attack is introduced. Same goes to slope of moment coefficient curve. The equation includes the effect of wing, body, and tail. From a result of calculation, a positive value is obtained. This means that the second criteria is fulfilled. From the calculation of last two sections, all of the slope of the pitching moment coefficient curve is negative, and the Cm0 is positive. Hence, the aircraft model is statically stable. Next, let's look into the total pitching moment about the center of gravity. Assuming linear curve for the moment coefficient versus alpha graph, the equation is shown as follows. Since the gross CG and forward CG are the same, the total pitching moment is calculated as follows. The figure shows that the design aircraft is stable as the slope obtained same as the theoretical slope. From the equation, the trim angle is obtained at 2.x at 62x, which means that the aircraft has to pitch 2.862x degree if it wants to maintain its altitude. The same procedure are calculated for MD wet CG and up CG. The figure shows that the aircraft is stable due to the slope obtained. Then the trim angle is obtained as 2.6156. Apparently, the angle of attack falls between the reasonable flight range. Therefore, the aircraft is longitudinal balanced as well as statically balanced. After that, the equation of neutral point is introduced. Neutral point is a point where the slope of moment coefficient is equal to 0. The stability criterion for longitudinal static stability is the position of the CG must always be forward of the neutral point. Then the neutral point is calculated. After that, the static margin is calculated. Static margin is neutral point value subtracted by CG value, which means that the larger the value, the more stable the aircraft. Recalling that the CG position must be in front of the neutral point, the value of static margin must be positive. The calculation is done for 4 CG positions. All often obtain positive value. Therefore, the aircraft is statically stable.
Next, I will move on to the lateral stability of our RC aircraft. The lateral stability is the stability about the airplane's longitudinal axis, which extends from nose to the tail. This helps to stabilize the lateral or rolling effect when one wing gets lower than the other wing on the opposite side of the airplane. The static lateral stability of an aircraft involves consideration of rolling moments due to side slip. If an aircraft has favorable rolling moment due to side slip, a lateral displacement from wing level flight produces a side slip, and a side slip creates a rolling moment tending to return the aircraft to wing level flight. By this action, static lateral stability will be evident. The principal surface contributing to the lateral stability of an aircraft is the wing. The effect of geometric dihedral is a powerful contribution to lateral stability. Dihedral angle is the angle between the plane of each wing and the horizontal when the aircraft is level. Wing position also greatly affects the lateral static stability. A high wing location gives a stable contribution. The direction of relative airflow increases the effective angle of attack of the wing into wind and decreases the effective angle of attack of the wing out of the wind, tending to decrease the rolling moment. Therefore, a high wing position usually requires no geometric dihedral. In our case, the RC aircraft uses a high wing and there is no dihedral angle. The rolling moment derivatives, which is CL beta due to the side slip, is given as shown in the slide. The wingtip shapes are as follows, and each of these wingtip shapes gives a certain value of delta CL beta. Since the chosen wingtip is the first one, our delta CL beta will be negative 0.0002 over radian, and our dihedral theta is equals to 0. Therefore, when the following values are substituted into the formula, we will get a CL beta of equals to negative 0.0002 per radian. Static lateral stability can be illustrated by a graph of rolling moment coefficient CL versus side slip angle beta. CL beta is the slope of the graph. Therefore, through calculations, the equation of the graph is obtained as shown, which is y equals to negative 0.0002x. Based on the equation, the graph is plotted, as shown in this slide. It can be seen from the graph that the aircraft is laterally stable. When the aircraft is subjected to a positive side slip angle, lateral stability is evident when negative rolling moment coefficient results. Thus, for example, when the relative airflow comes from the right, which will be a positive beta, a rolling moment to the left, which is negative CL, will be created, which tends to roll the airplane to the left. Lateral stability exists when the curve of CL versus beta has a negative slope and the degree of stability will be a function of the slope of this graph.
Now let's look into the communication signal of transmitter and receiver. Transmitter is used to produce radio wave in order to transmit or send data with the aid of an antenna. Figure shows the chosen transmitter in our project. Basically, there are two major band types, that is citizen band and independent scientific medical band. For CB bands, the frequency range from 27 MHz to 75 MHz. However, the frequency band is localized. It means that the frequency band is different from countries. For example, model aircraft usually has 72 MHz frequency band in USA. Various model aircraft in most European countries has 35 MHz frequency band. Nowadays, most of the RC hobbies use ISM 2.4 GHz bands, which range from 2.4 GHz to 2.4835 GHz. The main advantages of using this frequency band is frequency hopping spectrum FSS is used. It means that the system allows the transmitter frequency to jump between whole range of different channels. The data is transmitted when both of the transmitter and receiver hop to a common random sequence of frequency. In this project, we are using 2.4 GHz frequency band. This is because of the frequency hopping spectrum. At the same time, the frequency band produces a lower interference due to the frequency of any source of noise are automatically separated by the radio. Besides, it provides a higher performance level as more responsive control is offered due to its high data rate. The 2.4 GHz system consumes more lesser power consumption. For example, for the control range up to 250 meters, about 4 MW of power is consumed in 2.4 GHz system, whereas 35 MHz system consumes 759 MW of power. Last but not least, it requires a smaller antenna, which is 3 cm. However, there are some advantages of using the frequency band. For example, it is more susceptible to bad installation such as weak batteries. Besides, it is considered as a free-for-all band as various of other things such as Wi-Fi, wireless video centers, and other data links are shared in the band. Using 2.4 GHz system causes a higher cost as compared to 35 MHz system. For the channel is referring to each separate controllable function of an airplane. A typical aircraft consists of 4 channels, which is aileron, elevator, rudder, and throttle. However, a complex RC airplane may require more channels that control flaps, retractable landing gear, and so on. A total of 16 channels can be assigned with this transmitter. The figure shows the locations of switches. There are 3 positions in switches A, B, C, and D, whereas switches F and H possess 2 positions per switch. In our flight testing, only 4 channels are used, which are throttle, aileron, elevator, and rudder, to complete the primary control of the aircraft. The sequence of the channels included is AETR, which is the Futaba protocol. Table shows the assigned channels. Generally, there are 4 modes in the transmitter as shown in figures. However, most of the transmitters are using modes 1 and 2. In our case, mode 2 is used due to it is more commonly used so that the pilot can get used to the mode easily. The operation specification of transmitter is shown in table. From the table, the operating voltage indicates that 2 or 3 cells before batteries are accepted. This is because operating voltage of 2S and 3S before batteries indicates 7.4 volts and 11.1 volts. At the same time, the operating current is essential when connecting to external modules such as XZT, DJT, and R9M. Moreover, the output power indicates the actual power of a radio frequency that produced by the transmitter. For the features of transmitter, the transmitter has quad 4 bearing timbers which provides a smooth feeling to the pilot when moving the sticks. Second, audio speech output. From that, the various alarms and settings such as changing mode can be heard by the pilot to ease the flight testing process. Third, frequency telemetry capability that allows the pilot to access to the real-time flight data easily, such as battery voltage reading. Fourth, receiver signal strength indicator alert helps pilot to eliminate the problems of lost connection between transmitter and receiver by monitoring the reception quality of signal continuously and produce alerts before the quality becomes critical. Fifth, super low latency ensures the data messages are transmitted with minimal delay to minimize the probability of crashing the airplane. Last, OpenTX firmware allows to edit the setting and run radio simulation. For TX protocol, the system used in FreeSky is advanced continuous channel shifting technology. Besides, this system allows the frequency to be shifted hundreds of times per second. As a result, signal conflicts and interruptions are not involved in this system. Generally, the transmitter is able to compatible with FreeSky VX2 series, D series, X series, and L series receiver. Table shows the 3 RF modes of transmitter. In this case, the RF mode is set as D8 due to the receiver used is in VX2 series. Now, let's look into the receiver. Figure shows the chosen receiver. The main reason of choosing this receiver is it has the same frequency band of the transmitter, that is 2.4 GHz. Table shows the operation specification of receiver. Although the receiver can operate at a high range of wattage, the voltage supplied to the receiver is only 5 volts. This is because of the battery elimination circuit in ESC reduce the battery voltage to 5 volts to prevent short circuit from receiver. The operating current is important when calculating the endurance of the aircraft. The operating range indicates the distance of the transmitter signal that can be received. In short, the larger the range, the more effective the receiver. The universal RF protocol include PWM, PPM, and PCM. PWM is an analog signal where the pulse length indicates the servo output or throttle position. Usually, the length of the signal normal varies between 1000 microseconds to 2000 microseconds. However, this protocol is becoming less popular due to massive wiring, especially when more channels are required. Therefore, PPM is introduced with only one signal wire is used for solo channels. In this case, the series of PWM signals are sent one after another on the same wire. As a result, the received signal may not be as accurate as the serial communications. However, it is more popular and supported by many flight controllers. Furthermore, PCM is a data type similar to PPM. However, it is a digital signal. In other words, the value is between 0 and 1. The advantages of this protocol is it enables the signal error detection and even error correction. Therefore, the conclusion that PCM is more reliable can be made. Nevertheless, addition conversion of the signal is required and leads to a more expensive model. Serial bus is an exclusive RS protocol for FreeSky. In this case, up to 18 channels are supported by using only one signal cable. Basically, it's an invention of UART communication signal. For the feature, the receiver is able to compatible with all FreeSky modules that is in V8 mode and D mode. Therefore, the receiver can bind with the transmitter. However, it allows only one-way communication, which means that it can only receive the transmitted signal but cannot send the information back to transmitter. Last, it has a latency of 22 milliseconds. This value is considered small enough because of the flight speed is limited to 20 meter per second in our flight testing. Therefore, there is acceptable time gap for the pilot to recover the airplane if there is any incident happens. The electromagnetic signals are generated by the pilot by adjusting the gimbals. From that, the digital data is transmitted to the radio receiver. After that, the data is interpreted by the radio receiver. The stack of data is then sent to the particular destinations depending on the channels. Table shows the channels connecting with receiver and the wiring diagram is shown in the figure. Since the signals are traveled wirelessly, signal interference may occur. If the signals are weakened or completely prevented, the aircraft will lose of control and accidents or incidents may occur. There are some possible signal interference. First, physical objects such as trees, buildings, and other physical structures. The amount of RF signal that can pass through the walls is determined by the density of the wall. Second, radio frequency interference. In this case, RF range of 2.4 GHz system is used. However, there are many other devices use this channel such as microwave, cordless phone, and Wi-Fi device. As consequence, the device may cause noise and weaken the signal transmitted. Third, electrical interference. This interference comes from device such as computer, fans, or any other motorized device. Last, environmental factors. The signal can be weakened as they pass through a fog. Basically, there are two technologies to reduce interference. First, split spectrum technology. This technology requires the data signal either changing the data pattern constantly or alternate between two carrier frequencies. Therefore, the data is clearer and easier to be detected. This technology is divided into frequency hopping split spectrum technology and direct sequence split technology. In FHSS technology, the frequencies are changed in a predictable pattern by using narrow band signals. Frequency hopping means the data signal hop between narrow channels follow a predetermined cyclical pattern. Therefore, the technology is strongly resistant to interference and environmental factors. On the other hand, the SSS transmitter allows the spreading of signal over a full transmission frequency spectrum. The main characteristic of this frequency is redundant bit extent with sending of each bit of data in order to increase both safety and reliability. In this case, the impact of interference and background noise can be reduced. Although this technology provides greater security and signal delivery, it is a sensitive technology that may be affected by many environmental factors. Second, orthogonal frequency dimension multiplexing allows transferring of large amount of data over 52 separate and evenly spaced frequencies. As a result, crosstalk interference is greatly reduced by splitting the signal and transmitted over different frequencies. Basically, communication resolution can be defined as the magnitude difference between adjacent steps as shown in figure. It is also called quantization interval or quantum. By referring to the manufacturing data sheet, both of the transmitter and receiver have the channel resolution of 3072 steps. Generally, the process of converting oscillation electrical into electromagnetic radiation is done by using an antenna. At the same time, antenna also do the opposite work, which is the conversion of electromagnetic radiation into oscillation of electrical energy. Basically, most of the radio control system uses rubber ducking antenna. This is mainly due to its compact and very robust in the same time. At the same time, figure shows the components in the antenna, whereas the table shows the function of the components. This antenna consists of dipole antennas and are omnidirectional. In other words, the radio frequency energy can be propagated in 360 degrees in the horizontal plane. The radiation pattern when the antenna is oriented vertically is shown in the figure. The figure shows a radiation pattern resembling a donut shape that is symmetrical 360 degrees in the horizontal plane and the vertical beamwidth of approximately 75 degrees. Therefore, a 3D radiation pattern is shown in figure. Antenna gain is one of the performance measurements by considering the combination of antenna directivity and electrical frequency. In general, transmitting gain displays the efficiency of antenna converting the power input into radio waves in a specific direction. Whereas receiving gains describe the efficiency of converting arriving radio waves into electrical power. There are three units of the gains are shown in the table. To make sure that the receiver antenna can obtain the phase signal, both of the antennas should be kept as straight as possible to prevent reduction of the effective range. Second, the antenna should be placed perpendicular to each other. Therefore, the Third, the antenna must be kept away from conductive material by at least half inch. Last, the antenna must be kept as far as possible from ESC, motor, and other noise sources. Besides, to make sure that the module antenna can obtain the best signal, the transmitter antenna must be avoided from pointing directly to the model during the flight, as it will create a weak signal for receiver. Second, the antenna must be kept perpendicular to the transmitter's face, as a better RF condition can be created. Last, never grip the antenna during flight due to degradation of the RF quality.
Assalamualaikum. I bid to Dr. Nazri and Dr. Wan. My name is Nasiha and let me start the structural analysis on the wings of our RC plane. Wings are the most important component in an aircraft because wings generate most of the lift while moving rapidly through the air. The shape of aircraft wings are known as airfoil shape. Wings come in different configurations depending on the aircraft purposes. They are also attached to fuselage at different angles of attack and different position. In order for the wing to generate lift, it needs to be positioned at the correct value of angle of attack. A fixed-wing aircraft can have different number of wings, be it monoplane, biplane, quadruplane, and also multiplane. Monoplane is one-wing plane. So this diagram here shows the configuration for the different wing configuration for a monoplane. A monoplane is also the simplest one to be built. There are several wing positions, as can be seen from the figure, that distinguish every type of monoplane, which are low wing, mid wing, shoulder wing, high wing, and parasol wing. A low wing is the type of aircraft that has wings positioned on or almost at the bottom of the fuselage. By locating the wing down low, it allows a better visibility and releases the central fuselage from carrying wing spar. While a mid-wing is positioned midway up the fuselage is now bound to carry the wing spar and hence reduce the useful fuselage volume near its CG or center of gravity, where space is often in most demand. A shoulder wing is a category that is located in between mid-wing and high wing. The configuration for this type is that the wing is situated close to the top surface of the fuselage but not exactly on the top of the fuselage. Next is high wing. A high wing has its wing mounted on top of the upper surface of the fuselage floor. This is very different from the shoulder wing previously, and this shares many benefits and drawbacks with the shoulder wing, but the high wing has less visibility upwards on a light aircraft. And lastly, a parasol wing is the type of wing that is not being attached directly to the fuselage, but instead is being supported by struts or pylon. This configuration often needs additional bracing. As for as for the wing configuration for our RC plane, we use the aircraft type chose is the fixed wing monoplane. The reason why we choose monoplane, like I mentioned earlier, because it is the easiest one to be built. And then in addition to that, a monoplane is the most common configuration since it has the highest efficiency and lowest drag. Okay, apart from that, the high wing is being picked instead of low wing because low wing aircraft is prone to incur more ground effect during the landing as compared to the high wing. And then for the airfoil type, we choose the M15 and we have 1.4 meter of wingspan with 5 aspect ratio of 5, and also wing chord. Our wing chord we chose 0.28 to be our wing chord. Next, moving on to the aileron configuration. According to the previous study, aileron should take about 5 to 10% of the wing area. The ratio of aileron chord to wing chord must be about 15 to 25%, and the ratio of aileron span to wingspan must be around 20 to 30%. Therefore, for this aircraft, we choose the area to be 5%, the aileron area 5% of the half wing area, and the chord is 20% of the half wing, span 25%, and inboard span is 70%. And this is the illustrated wing of our aircraft together with the aileron. Okay. A structure has the purpose of carrying loads that it was designed for. In order to do so, it needs to be able to transfer the load from one point to another. For an instance, the load is being transmitted from the location of the load to the supports. This is done by developing a system called internal force system, and the distribution of these internal forces must be identified before the stress distributions can be calculated respectively. So in structural design, knowledge about stress is very important since any members in the structure must be able to withstand the maximum amount of load exerted on its cross-sectional area so that the stress will not cause breakdown in the crystalline structure of the material, or simply state a structural failure. Okay, on top of that, strains and displacements are also needed to be calculated in order to make sure that the member in the structural system retains adequate rigidity of stiffness as well as strength to avoid distortion. Before I go further, let's take a quick look at the weight and lift distribution of the wing and fuselage. By referring to the front view of the plane shown here, we know that this aircraft is symmetric. Therefore, the analysis is done on half wing only. The analysis is done on half wing since they are symmetrical. Now, the free body diagram can be illustrated as a cantilever beam, and therefore the weight of the wing and the fuselage, the wingspan and the width of the fuselage need to be divided into half. Only then the weight distribution can be calculated precisely. Now that the dimensions of the aileron has been determined, the next step is to identify the strength of the wing with and without ailerons so that the material can be chosen properly. The stresses can be obtained by drawing the shear force and bending moment diagram for the mentioned structures at cruising speed with different load factors, which are G equals to negative 1.5, the first case. Second case is 1G, and the third case is 3G, the maximum load factor. Since the analysis is taken for cruising state, therefore the lift is assumed to be equal to the weight of the aircraft. For the first case, G equals to negative 1.5, as referred to this slide, the maximum shear force exerted on the structure is at the central fuselage. The force is then decreased substantially until reaching 24.4018 Newton at the wing fuselage attachment before becoming zero at the wingtip. The same trend can be seen for the bending moment, where maximum bending moment occurs at the center fuselage before increasing slowly until it finally reaches zero at wingtip. The same goes while for the second case, or 1G, we can see here that the maximum shear force is not at the wing fuselage attachment, but instead at the the center of the wing with uh, an amount of value negative 2.3234 kilopascal shear stress, while the bending stress is 167.801 kilopascal. As for the third case, G equals to 3, by referring to this figure, the central fuselage once again also becomes the most crucial part, as it needs to withstand the highest amount of shear force and bending moment before finally reaching zero at the wingtip. The reason why central fuselage needs to withstand the largest amount of force and moment is because it acts as support system to the cantilever beam. As mentioned earlier, we illustrated this problem as cantilever beam. As for the wing with ailerons, the first thing to do is to find the lift generated by the aileron. The lift can be calculated by by using the usual lift formula L equals to half rho v square S CL. Since this analysis is done during the cruising state, therefore CL during cruising needs to be determined by finding out its respective angle of attack. In this case, the angle of attack during cruising is alpha equals to 2.8. So the CL is 0.7173. By substituting all the values, we now can obtain the lift produced by the aileron. The lift distribution on aileron is then can be also calculated since the lift generated by aileron is known by dividing the lift with the width of the aileron. The same analysis is done on the wing with ailerons, which consider three cases, the same cases, negative 1.5G, 1G, and also 3G. The trend as for the wings with aileron seems to be similar to without aileron, but with different value of stresses. Okay, for an example, by looking at the figure here, the maximum shear stress is 4.0208 kPa, while maximum bending stress is 277.666 kilopascal. This data isn't compared with the second case, which is referring to this figure. From here, we can see that the maximum shear stress should be exerted on the wing is 2.6064 kilopascal, while bending stress is 200.9617 kilopascal. Finally, for the third case, or the maximum load factor, which is 3G, as illustrated here, the wing should withstand the highest stresses, which are 7.908 kilopascal for shear stress and 582.526 kilopascal for bending stress. We can see here from table shown that wing with aileron should be able to withstand a slightly more stresses than one without aileron, or in simpler words, wing with aileron should be stronger than without aileron. This is because aileron is just like flaps. When we lower the aileron, it means that the chord line of the wing has also changed. This results in producing a higher angle of attack. Therefore, as the angle of attack increases, the lift is also increases as they have a linear relationship. This increase in lift will simultaneously cause the increase in induced drag. In short, the wing with aileron should be stronger than without aileron. It's because it needs to withstand the addition, lift, and drag generated by the ailerons. Next is the lift distribution of aileron at different angle of attack. The lift distribution of aileron is calculated at different angle of attack and its respective velocity is identified afterwards. The lift is calculated by using the formula L equals to n cos alpha minus a sin alpha, where alpha is the angle of attack and n is the integration of pressure on the upper and lower surface from the trailing edge to the leading edge of the airfoil. Same goes to the A. Okay, based on the elevation of our aircraft at 10 meter, the following parameters are identified. First, which the pressure for the lower and upper is the same with 1.01 times 10 to the power of 5 Pascal. The temperature is at around 288 Kelvin with the density of 1.225 kilogram per cubic meter. Okay, first the free stream velocity need to be identified. Only then the lower and the upper shear stress acting on the airfoil of the aileron can be calculated by using the following equation. Mu du dy. Mu is the dynamic viscosity. So after substituting all the respective values, now we obtain the value of shear stress, and then by referring to this equation, we substitute back the respective value. Okay, based on table shown here, it can be seen that the coefficient of lift is negative as the angle of attack is negative. However, as the angle of attack increases, the coefficient of lift also increases. This trend differs from the velocity trend. velocity trend. The highest velocity is when the aileron is deflected at 2 degrees with 2.7437 meter per second, while the lowest velocity is when the aileron is not being deflected. In short, we can say that both of the lift and the angle of attack of the aileron has been proven to have a linear relationship.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Amira binti Muhammad Asmi. So I'm going to talk about wing loading. So strength approximation method has been used to calculate the wing loading for this aircraft. The calculation has been made at the half wing of the aircraft, and the half wing was divided into 18 stations. So basically, this is the important data that has been calculated in order to plot the wing load distribution coefficient, local lift coefficient, shear force and bending moment versus distance of the wing. So this is the local lift coefficient versus distance of the wing. As we can see here, the local lift coefficient obtain higher value at the root chord of the wing and decreasing at the tip chord of the wing until zero value. As we all know, the tip chord of the wing will produce less or to zero lift force, or maybe will never generate lift. So this is the the wing load distribution coefficient versus distance of the wing. It is obtained the similar pattern as the previous graph. The higher value of wing load distribution coefficient obtained also at the root chord of the wing and decreasing until the tip chord of the wing. So this is the the comparison between the wing load distribution coefficient and the elliptical graph versus the distance of the wing. The wing load distribution coefficient is based on the strength approximation method. Meanwhile, the CY is based on the elliptical graph. So as we can see here, the elliptical obtain the higher value than the strength approximation method. So this is the shear force versus distance of the wing. As we can see here, the higher value of shear force obtained at the root chord of the wing and decrease until the tip chord of the wing. Now similarly with the bending moment versus distance of the wing, it has similar pattern with the shear force versus distance of the wing. The bending moment also obtain higher value at the root chord and decrease until it reach the tip chord of the wing. Thank you.
Okay, I will talk about the wing molding. What is the wing molding actually? Wing molding is a method that how to attach a wing on the fuselage. Okay, there are several type of wing that we can see in nowadays. Low wing is the wing molded near or below the bottom of the fuselage. Mean wing is the wing approximately halfway out of the fuselage, and shoulder wing is the wing molded on the upper part of or shoulder of the fuselage, slightly below the top of the fuselage. And parasol wing means the wing is rise clear below upper rise clear above the top of the fuselage. And last but not least, the high wing that we decide to use in our design is the wing mounted on the upper fuselage. Next, in our study, we found that there are normally two methods that people use in UAV, or we call RC plane. First is they use rubber bands, and second they will use screw. Okay, the rubber band method actually is very simple. They only need rubber bands and bamboo stick. First of all, they pieces the bamboo stick through all the foliage, and then put the wing upper the foliage and use the rubber band and tie it. It's simple. And when we talk about rubber band, we will talk about elasticity, and the idea of the elasticity of the rubber band is E is the energy stored in the rubber band, equal to half of the spring constant times with the distance square. In this case, we found that the rubber band spring constant is 17.38 Newton per meter, and our wingspan is around 0.28 meter. So we will get the energy stored in the one rubber band is 0.68 joule. Okay, next is screw. Screw method need a piece of plywood, and normally 2, 3 or 4 screw will needed. Okay, the method also simple. First of all, we need to put the piece of plywood on the foliage, and then we put the wing above of that, then we screw it, and that's all, that's all. Okay, then the properties of the screw that we found in Mizumi show that the smaller size of the screw, which is M4, can produce maximum allowable load is 114 kilo force, which is very enough in our case. Okay, next let me talk about the comparison about rubber band versus screw. The rubber band is more easy to assembly and disassembly when we want to take off our wing, or we need to assembly back the wing. That is more easy. And the rubber band method is more lighter, less wet, and but the rubber band method is only suitable to the small RC plane, because when the rubber band is pulled too tight, they will become not long last user. Okay, and next the screw. The screw will be very long lasting and more stronger, can apply to large RC plane. But in our case, we will decide to use rubber band method because our aircraft is not that big, and then we planning to reduce the weight that on the aircraft, so we will select the rubber bands methods.
Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad Imran Aiman bin Idris. So today I want to present the fuselage part. So fuselage contribute very little to lift and produce more drag, but it is an important structural component. Serve the purpose of housing or accommodating practically all equipment, accessory and system in addition to carrying the payload. Provide sufficient number of cutout in the fuselage for access and inspection purposes. The reaction produced by the wing, tail or landing gear may be considered as concentrated load at the respective attachment point. So this is the first type of shear flow diagram, which is for the 3G. So it shows that from the graph, it shows that the maximum stress is around in the middle of the wing, with the maximum value of 1603 Pascal. So next is the bending moment diagram for type 1, which is the 3G. From the graph, it shows that it has 24,000 Pascal for the bending moment. Next is for the type 2, which is using the negative 1.5 G. So from the shear flow diagram, it shows that the maximum value of stress is concentrated at the middle of the wing, which is with the value of 801 Pascal. For the bending moment diagram, uh, for the type 2, it shows that 20,000 kilopascal, and it occur around the middle of the wing. So we move on to the structural analysis. So the table show the material property of the aircraft, which is the aircraft being fabricated by the firm, and the value of the characteristic is based on the test that been run to get the exact result. The analysis is run by the FIMAT National Software Simulation. So from the test that we need to require the characteristic of the firm, it show that from the every part has a individual weight, which is the tail is 4 Newton, and next for the wing is 8 Newton, and lastly for the fuselage 4.51 Newton. So it sum up of the overall fuselage weight with the 32.36 Newton for overall fuselage weight. So we move on to the first step of the structural analysis. First, we need to mesh our component, which is the fuselage. So we need to set up, if possible, we need to set up the meshing size is in the smallest size that we can do for the software, because if we can get a smaller size of the meshing, it will be more accurate in terms of the simulation and the exact location of the stress. So this fuselage is been set with 0.779 in size to ensure this analysis can be proceed to another step, because meshing is the first step to begin the structural analysis. So this is the result of the analysis that been used the von Mises stress distribution along the solid. The contour is been set by the typical von Mises. So from the result, it show that the side of the fuselage have 0 to 2 stress, which is it is so low because from this static analysis, no no force is at x direction because all of the load or the weight is in y direction for overall part. So in this result, the maximum value of stress that can occur in this component is 16.66 Pascal, which is the highest value. With it show that the highest value of stress that this fuselage need to withstand. On the top of the fuselage also have a stress around 8 to 12 Pascal, which is it is affected from the wing and also the tail. So from this result we can see that the maximum value of stress is around the root of the landing gear, both landing gear, front and back landing gear. And to be precise, the maximum value of stress is around the root. This is because all the concentration load, all the load is be concentrated at the both of the landing gear. That this fuselage need to withstand 16.66 Pascal. Around the root of the fuselage also have numerous value of stress from the 4 Pascal until the maximum value, which is 16.6 Pascal. So from this overall value, stress show that this aircraft is still safe and strong to fly in normal condition. So that's all from me. Thank you.
Okay, my name is Melvin John, and next I will talk about the compressive and shear buckling analysis, which is done on our former structure and buckled structure of our RC aircraft. So this slide shows the equation for elastic instability of flat sheet plate, which is used to calculate the compressive buckling analysis, where the Kc is buckling coefficient, which is referred to the coefficient for flat rectangular plate for Brun. E is modulus of elasticity, V is elastic position ratio, B is short dimension of plate, and T is sheet thickness. So the first analysis is done on the former structure. The aspect ratio formula used is A over B, which is 168 over 94. 168 over 94 is our former structure dimension, and once we calculate, the value we get is 1.78, and 1.78 is used to refer to the graph of compressive buckling coefficient to get the Kc value, which is 5.8. Then these two value is substituted into the critical elastic compression buckling stress equation, and we obtain the value is 21.446 megapascal. Next, we calculate the safety factor. The formula used is critical buckling stress over maximum stress. The critical buckling stress that we obtained just now is 21.446, and 16.6 is the analysis done using software FreeMac, and we get is 16.6. Once we substitute, we get 1.29 megapascal. Then the margin of safety is calculated, which is 0.29. Since the buckling stress is 21.45 megapascal, which is greater than the maximum stress experienced by the structure, which is 16.6. Thus, the former structure will not buckle. The positive value of margin of safety also show that the structure is safe. Next, we calculate for the buckled structure. The step is repeated same as before. The aspect ratio we get is A over B, which is 100 over 100, which is the size of our bucket used. And refer to the graph, we get the Kc value is 6. Then we substitute the value and we find the critical elastic compression stress is 18.9496. Then we calculate the safety factor, we get 1.14 megapascal. And the margin of safety we get 0.14. Since the buckling stress is 18.95 megapascal, which is greater than the maximum stress experienced by the structure, thus the bucket structure will not buckle. The positive value of margin of safety also show that it is safe. Next, we do the analysis of shear buckling, and this slide show the equation that we use, and the Ks is the shear buckling coefficient, which is referred to Brown coefficient as flat plate, and E is modulus of elasticity, V is elastic portion ratio, and B is short dimension of plate, and T is thickness. So as before, the aspect ratio that we calculate for former structure is 1.78, and we refer to the graph for shear buckling, we get Ks is 6.7. Then we calculate the critical elastic shear buckling, we get 23.9480. Then we calculate the safety of factor, we get 1.44 megapascal, and the margin of safety obtained is 0.44. And from there we can conclude that the shear buckling stress is 23.95, which is greater than the maximum shear stress experienced by the structure. Thus, the former structure will not buckle. Margin of safety also is positive. We show that it's safe. The structure is safe. Next, the step is repeated for bulkhead structure, and the aspect ratio is 1, and we refer to the graph, we get the Kc value is 9.8, and the critical elastic shear buckling stress is 30.9511 megapascal, and the safety factor for bulkhead is 1.14 megapascal, and the margin of safety is 0.14. And since the shear buckling stress is greater than the maximum stress experienced by the structure, thus the bulkhead will not buckle. The positive value of margin of safety show that structure is safe. And next, we also done the fuselage shear and fracture analysis, and by considering the fuselage to be symmetrical, the conceptual structure analysis is considered as below shown. So this diagram shows the configuration of our aircraft, and we calculate the moment of inertia at station 0 about centered y-axis. The formula used is Iy equal to I0 plus AH square, and I0 is neglected because the value is small. H is the height of stringer, and we calculate the value and we get is 5.0226 inch. So this table show the necessary calculation in order to determine the flange bending stress and net total shear load to be taken by the cell skin. And this the table the below one show the fuselage shear flow and the calculation for flexural shear system. So from these two tables we can conclude that all cell obtain safety factor that exceed 1, and the skin of the aircraft or fuselage can withstand the applied torsion.
A very good morning, everyone. Today I will be presenting about landing analysis. I myself, Steven Technology, will be presenting about landing analysis. As you can see, this will be the back landing gear on the left hand side, and the right hand side will be main landing gear. Will be the exploded view. The back landing gear is included with connected to the body, which is the connector which we use to connect from the body and to the strut of the bicycle, and we include the rim for the tire and also the tire itself. And for the main landing gear, there is a stainless steel frame which is banded into V shapes, including with strut and tire and rim, to make it more stronger and more reliable. What we use to analyze is using a SolidWorks 3D model. This is used to create the simulation of the analysis by using some certain boundary conditions. Certain boundary conditions such as the fixed points. The fixed points we are for the back landing gear. The fixed points will be used at the rim side, at the tire side. So the tire will be our fixed point, while the load will be applied on the top of it, where the connection between the strut and also to the fuselage. Another, in the main landing gear, we will be connecting the top of the with the where we connect fuselage and also the landing gear, we will use as a fixed point. As we use as a load point, the fixed point will be at the tire. The material properties. This is a back landing gear material properties. What we're using is a stainless steel. This is as you can see, the default will be a max of 1 Mrs. Stresses. That will be what we will be analyzing. The yield stress, as you can see, is a 1.72339 10 to the power of 8 Newton meter square. The stainless tensile strength will be 5.13613 10 to the power of 8 Newton meter square. The elastic modulus will be 2 10 to the power of 11 Newton meter square. The Poisson reserve will be 0.28. The mass density is 7,800 kilogram meter per cube. As we move on, this will be the material properties for the main landing gear. As you can see, it's almost similar, but it's a slightly different with the stainless steel properties. As you can see, the slight difference will be at the yield stress. Yield strength will be the 2.3442 10 to the power of 8 Newton meter square. The tensile strength will be 6.20 10 to the power of 8 Newton meter square, and elastic modulus will be 1.93 10 to the power of 11. The Poisson ratio will be slightly lower, 0.28. The mass density will be 8,000 kilogram meter cube. As you can see, this will be the result we obtained from the SolidWorks analysis. As you can, this is the 1 Mrs. stress analysis. As you can see, where we applied the fixed point will be the blue color, while the red color will be the where we applied forces, which is the 33 Newton, which is determine the weight of the fuselage and overall body. As you can see, the bending will be mostly occurred at the top of the model, so the down will be more stronger. As you can see, for the main landing gear, the most of the bending will occurs at the where we apply the forces, which will be the fuselage. So the structure of the tire will be holding it more firmly. That's all for me.
Hi, good day to all of you. I'm Shata, who's from Group 3. First of all, glad to meet all of you here, and I would like to welcome everyone to enjoy the presentation. I'm here to present to you on the research and design I had proposed for the infinite analysis. Before let me start my presentation, please allow me to brief you on what I'm going to talk to you all today. In this presentation, I will be covering on the infinite analysis, which comprises of an introduction, preliminary sizing for the horizontal and vertical stabilizer, as well as control surfaces that are attached to it with their respective theoretical analysis. Besides that, it's my opportunity to explain to all of you regarding the strength of adhesive on the joint between the tail and fuselage. Generally, the empennage is the whole tail unit at the extreme rear of the fuselage that provides the stability and directional control of the aircraft. It consists of the entire tail assembly, including the vertical stabilizer that prevents the side-to-side or yawing motion of the aircraft nose, horizontal stabilizer that prevents the up and down or pitching motion of the aircraft nose, rudder that used to control yawing motion, elevator that used to generate and control the pitching motion, and finally the rear section of the fuselage. For the preliminary horizontal and vertical tail sizing, before the basic parameter and sizing were done, it is vital to choose the appropriate empennage shape that suit for the aircraft function. Since our team has planned to design UAV aircraft that carries 5 kg of load, it is more appropriate to set the conventional configuration with a low horizontal tail. This is because roots of both horizontal and vertical surfaces are conveniently attached directly to the fuselage, and effectiveness of the vertical tail is large because interference with the fuselage and horizontal tail increase its effective aspect ratio. Once the proper and finished shape is chosen, I proceeded a detailed research on the sizing of the horizontal and vertical tail. To do so, the following parameters, which are displayed on the table, were chosen. The values of each parameters are set based on the research on the previous aircraft design that are used currently. Since my team has chosen Extra 330 SC model, so I decided to do a parametric study on the aircraft and interpret the value based on my team's suggestion and ensures the values can sustain the 5 kg of load. So, from this table as shown here, and these are the basic parameters I have found, and the calculations and dimensions are interpreted and predicted based on the chosen Extra 330 SC model. So, the parameters which involved for the horizontal tail sizing are chord, span, tail area, aspect ratio, aerodynamic center, center of gravity, horizontal tail weight, maximum coefficient of lift. Similarly, the same principle also being applied for the vertical stabilizer sizing, in which these are the parameters that I have found based on my prediction. So the parameters involved for the vertical tail sizing are chord, span, tail area, aspect ratio, aerodynamic center, center of gravity, vertical tail weight, and finally maximum coefficient of lift. Now, I would like to explain to you on the horizontal and vertical stabilizers theoretical analysis. To analyze the structure can withstand the load and other forces. The effectiveness and strength of both the stabilizers were calculated and predicted. The effectiveness of the stabilizers are or can be predicted by means of calculating the tail volume ratios, where whereas for the strength of the stabilizers, I calculate the shear and bending stresses acting at varied load factor. Okay, from the calculation, the output of the horizontal tail volume ratio is as follows. The figure on the left shown how the horizontal tail volume is calculated, whereas the table on the right shows the extraction of information based on our design to calculate the horizontal tail volume ratio. From the calculation, I obtained the horizontal tail volume ratio of 0.5. To check whether the results are reasonable, proper references are referred. This is as follows. Based on the table, by referring to the Raymer 1992 sources, the tail volume ratio for the horizontal stabilizer, which is 0.5, is much reasonable and effective, as it can be compared from the table above under the civil propeller aircraft type and the category of home build, where home build can be defined as an amateur built aircraft or kit planes that are constructed by persons or people for whom this is not a professional activity. Similarly, the output of the vertical tail volume ratio is as follows. The figure on the left shows how the vertical tail volume ratio is calculated, whereas the table on the right shows the extraction of information based on our design to calculate the vertical tail volume ratios. From the calculation, I obtained vertical tail volume ratio of 0.5. 0.04 for our design. To check whether the results are reasonable, proper references are referred. This is as follows. Based on the table, by referring to the Raymer 1992 sources, the tail volume ratios for the vertical stabilizer, which is 0.04, is much reasonable and effective, as it can be compared from the table above under the civil propeller aircraft type and the category of home build. Open completion of a proper sizing of the stabilizers based on the available criteria. The strength of the stabilizer is also need to be theoretically determined for the proper material selection of the design, which depend on the physical and mechanical properties of the material. Hence, this can be achieved by comparing the local stresses of the stabilizers at cruising speed by the different load factors, such as G is equal to negative 1.5, 1, and 3.0. The lift is assumed to be equal to the gross weight of the aircraft due to the calculations are made at cruising speed. The graphs of three load factors for the horizontal tail are plotted, and shear and bending stresses are calculated together with a proper free body diagram on the right as follows. Similarly, the graph of three load factors for the vertical tail are plotted and shear and bending stresses are calculated together with the proper free body diagram on the right as follows. Okay, firstly, this is the horizontal stabilizer free body diagram, which is shown on the left, as well as the shear and bending moment diagram plotted on the right for or at G is equal to 1.0, and the shear and bending moment stresses also calculated based on the maximum shear and bending as shown from the graph. This is for G is equal to negative 1.5 for horizontal stabilizer. So the shear stress and bending stress also calculated based from the graph, and you can refer to the free body diagram on the left. And it also similar process has been approached for G is equal to 3.0. We also done the same process as we done previously for the G is equal to negative 1.5 and 1.0, and now we are moving on to 3.0, and the shear and bending stresses also calculated based on the graph, and the values are depicted on the right of the graph. And now we are moving to the vertical stabilizer shear and bending moment diagrams. So as the same principle also being applied as we have done for the horizontal stabilizer. So here the values, only the differences is the value of shear and bending stresses. Otherwise, and one more, a few changes that I have done is the drawing of the free body diagram. If you see for the horizontal stabilizer, it is not been projected horizontally, because horizontal stabilizer is really or naturally has been projected horizontally, so we don't have to project that horizontally. But vertical stabilizer, to make the calculation easier, I project the vertical stabilizer in a horizontal manner so that I can easily plot the shear and bending moment graph at different load factors. So this is the shear and bending moment diagram as well as the free body diagram for the vertical stabilizer at G is equal to 1.0, and I also calculated the shear and bending stress for based on the maximum shear and bending moment. So next is G is equal to negative 1.5 for the vertical stabilizer, and finally followed by G is equal to 3.0 for the vertical stabilizer. For a safe flight, sufficient amount of forces should uphold the shear and bending stresses of the stabilizers without damaging the structures. This is in turn leads to a proper selection of materials as our design of stabilizers are constructed using EPP form. To determine whether the structures can withstand above stresses, the buckling stress under shear and bending loads of the selected material, which is EPP form at a density of 20.8 kg per meter cubic, is calculated based on the available data of the selected material. The calculation of the buckling under shear and bending loads are as follows. Firstly, the parameters that need to be substituted into the equation as shown below are obtained from the manufacturer's technical data. The values are interpolated based on the density of EPP form. Once the parameters are collected, it is substituted into the equation below and plastic correction is made based on the graph. The graphs are illustrated in the final report, which is under the appendix from P to K in the reports. Based on the obtained data, the maximum shear stress and bending moment when comparing at 3 load factors are tabulated and it is compared with the buckling stresses under shear and bending loads. From the table, we can conclude that all the theoretically calculated shear and bending stresses are less than of the buckling stress under shear and bending loads. This can give a confidence that the structural integrity that the structure can manage to sustain both the shear and bending load acting on the surface of the stabilizers at different load factors are not affected, and the structure are said to be in airworthy condition. Apart from that, tear strength, which is the ability to withstand the effect of tearing, are also tabulated below the shear and bending stresses. The calculated tear stresses is much lower than of the tear strength suggested by the manufacturer of the EPP form. In designing of the control surfaces, both rudder and elevator, the processes are exactly similar as we imposed on the designing of the horizontal and vertical stabilizer. This process includes selection of airfoil in which the NACA selection should be same as imposed on the stabilizer, which is NACA 0012 due to the symmetrical airfoil section characteristics and determination of control surface sizes based on the available current aircraft design that matches the mission of the aircraft. However, the theoretical analysis is different since the control surfaces can deflect up to certain angle. To ensure that the control surfaces can perform at different angle of deflection and load factor, proper dimension or sizing of the control surfaces are vital that have proper justification. These are the parameters that involve in proper designing of the elevator. To check whether the results are reasonable, proper references are referred. From the table above, the length of chord of elevator is 0.09 meter, can be obtained by calculating the ratio between the control surfaces over stabilizers. To do so, the ratio between the control surfaces over stabilizers are set to the average values as shown from the reference above, which are 0.45 for the elevator for the home built aircraft category based on the ROSCAM 1985. On the other hand, from the references of 1992 about Raymer 1992, about 90% of the tail span, elevator design and construction are beginning from the side of the fuselage and extend to the tip of the tail. Hence, by mathematically express the statement which is 20% to the tail chord, we can obtain the value for the elevator span which is 0.54 for the elevator. The hinge distance for the elevator to assemble with its horizontal stabilizers are calculated by multiplying the chord length with 20% of the control surfaces where the values from the control surfaces leading edges are depicted as in the table. So the inch axis length is 0.05 from the leading edge of the elevator. For the rudder design and sizing, the similar process is approached. The ratio between the control surfaces over stabilizers are set to the average value as shown from the reference above, which is 0.47 for the rudder for the home-built aircraft category based on Roscom 1985. On the other hand, the rudder span will be 0.24 as well as the hinge distance for the rudder to assemble with its vertical stabilizer is 0.02 from the leading edge of the rudder. For the theoretical analysis, in order to obtain the lift at different angle of attack, the cross-section of the control surface and free body diagram are drawn, which are shown as follows. The flow which passes off the trailing edge is assumed to be as on the diagram for calculation purpose. Hence, from the free body diagram, we can calculate the lift force on the control surfaces based on the formula as follows. However, such formula is not fulfilled if axial force A and normal force N are determined. To do so, the two formula which is below the main formula is approached. In calculating the normal force and axial force, the following parameters are calculated as follows. The parameters are calculated by means of the interpolation from the atmospheric table based on the elevation of the aircraft, which is 10 meters from the ground. So from this slide, we can observe that there are few parameters which involve in the calculation of the axial and normal force. So the parameters which involve in the calculation of the formulas are pressure, temperature, density, dynamic viscosity, and free stream velocity, as well as the shear stress on the surface. So for the lift coefficient, the values of lift coefficient at an angle of attack is calculated by means of referring to the introduction to aerodynamic sources based on the thin aerofoil theory for symmetrical airfoil. Upon calculation of all the variables, the results are tabulated as follows, and graphs of lift against angle of attack and velocity against lift is drawn. Based on the analysis of the lift versus angle of attack and velocity versus lift, we can observe that increasing in angle of attack causes increasing of lift as well as lift coefficient. On the other hand, deflecting the control surface downwards from the stationary position causes the velocity to increase, whereas on the opposite direction of the deflection of the control surfaces, which means upward motion of the control surface, the velocity drops gradually. The maximum lift exerted on the elevator at an angle of attack negative 25 degree is 0.0441 Newton, which have the velocity of 0.7247 meter per second. Whereas for the rudder, the maximum lift exerted is 0.04444 at an angle of attack, which is 25 degree, with the velocity of 1.1498 meter per second respectively. To determine the torque generated by the control surfaces, we can compare the maximum lift generation on both control surfaces multiplying with the length of the push and pull rod which is connected to the servo motor. These values are eventually compared with the servo torque in order to determine the effectivity and efficiency of the servo motor. The mathematical expressions to calculate the torque for rudder and elevator are as shown on the slide as follows. For our design purpose, the proposed glue for the attachment between the fuselage and horizontal and vertical tails are by means of using Gorilla Glue. The figure shows the physical properties of the glue as well as its benefits. By comparing the theoretical shear stress with the shear strength of the glue stated above, which is 3,500 pound per square inch, which is equivalent to 24.13 megapascal. The glue has high tendency to withstand the calculated shear stress, and this in turn can make a conclusion that the structural integrity of the attachment between tail and fuselage are maintained to an airworthy condition. In terms of weaknesses and challenges, the main factor contribute for the problem is the environmental factors such as high wind flows. During this stage, the theoretical estimation is not accurate as the control surfaces are tossed by turbulence. This in turn will cause fatigue to occur on the structure, both stabilizers horizontal and vertical, respectively, and the control surfaces rudder and elevator respectively, that eventually affect the integrity of the structure and causes crack and breakage of the structure. Now, we are in the end of my presentation. I would like to thank all of you for lending your ears, and I hope that you have spent your time meaningfully by listening to my presentation. Thank you so much.
Hello everyone, my name is Shagantan and Balakrishnan, and I'll be continuing the presentation on flight testing and planning. So the first thing, what is flight testing and planning? Flight testing and planning is the developing and gathering of data during flight of an aircraft or atmospheric testing of launch vehicles and reusable spacecraft. After you obtain this data, you analyze the data to evaluate the aerodynamic flight characteristics of the vehicle in order to validate the design, including safety and other aspects. So flight tests consist of two major phases. The first would be finding and fixing any design problems, and the second would be verifying and documenting the vehicle capabilities. The flight test phase can range from the test of a single new system of an existing vehicle to the complete development and certification of a new aircraft. So there's four parts in flight testing. The first would be the pre-flight test. Now I'd like to talk about the pre-flight test in terms of the aircraft. So we have to always do a detailed check on the plane and take time over it. This is because if the aircraft has been checked or painted, we have to pay careful attention to these activities as they can give rise to numerous technical issues such as pitot or sensor damage. The other thing is to allow certain ground checks to be completed prior to flight clearance, and we have to think carefully about the weight and center of gravity for the check flight. Expect the aircraft will inevitably be much lighter than the aircraft online. There may be no problem here, but think about it and consider speeds to be used in relation to stall speed and minimum control speed. The next would be airfield. The airfield can be used as rarely a choice matter, but it is wide to consider any implications stemming from the airfield itself. The runway capability and its effect on performance, high ground and obstacles, all need to be considered as well as the general operational situation. Moving on to the weather. During certification development flight testing, the weather criteria often drive the ability to carry out a given test. However, in the check flight world, it is rare to have privilege of waiting for the perfect weather. That said, it is certainly wise to know what the bottom line is for the checks to be unknown. And finally, checklist. The check crew will need to think and work on the standard checklist, and of course they have to understand and recognize the importance of the checklist. So this would be an example of the RC airplane pre-flight checklist created for this group. So there are items, the descriptions, and completion. So we just have to tick according to the items whether it is completed or not. So the items include covering and surface, landing gear, propeller, motor, electrical connections, screw, servos and linkages, receiver, transmitter, balance and center of gravity, control surfaces, ailerons, and rudder. They have their own descriptions, and all we have to do is refer whether all this is on par with our RC flight. Now moving on to the next part. The next part is preparation. Flight test preparation begins well before the particular aircraft is ready to fly. The instrumentation parameters recorded during a flight test for this project are: first will be atmospheric pressure and temperature, dynamic pressure and temperature measured at various positions around the fuselage, structural loads in the wings and fuselage, aircraft altitude, angle of attack, and angle of side slip. These are all regarding angles. Next will be the acceleration in all 6 degrees of freedom measured with the accelerometers at different positions in the aircraft. And finally, the battery performance parameters in terms of pressure and temperature. So these are the parameters that we would consider during the preparation. The third stage would be execution. So when the RC plane is completely assembled, ground testing is then conducted. This allows exploring multiple aspects of the airplane, such as the basic aircraft vehicle operation, battery performance, and it provides a first look of structural loads. The several aspects to a flight test program are handling qualities, which evaluates the aircraft's controllability and response to pilot inputs throughout the range of flight. Next will be performance testing, which evaluates aircraft in relation to its projection abilities, such as speed, range, power available, drag, and so forth. The other will be avionic or system testing, which verifies all electronic systems performed as designed, and structural loads that measures the stresses on the airframe, dynamic components, and controls to verify structural integrity in all flight regimes. So emergency situations are evaluated as a normal part of a flight test program. For example, battery failure during various phases of flight, such as takeoff, cruise, landing, and system failures. The primary goal of a flight test program is to gather accurate engineering data, often on a design that is not fully proven. Moving on to the fourth stage, which is analysis and reporting. So, analysis and reporting is to analyze the internal and outer part of the flight by checking all parts. Reporting includes the analyzed data result. We could record the flight data and create performance charts based on the behavior of the aircraft during the flight test. By using these performance charts, a pilot can determine the runway length needed to take off and land and the time required to arrive at the destination. It gives them a general overview of it. The data from the charts will not be accurate if the aircraft is not in good working order or when operating under adverse conditions. Each aircraft performs differently and therefore has different performance. Every chart is based on certain conditions and contains notes on how to adapt the information for flight conditions. Moving on to the flight test location. So this is the Google Map image on where we would conduct the flight test, and this is the exact location where we got the picture of it, which is the UTM marching paddock, also known as Padang Kawat UTM. So the flight test location will be defined as a total airspace that model aircraft which will always stay within while in the air. It should be clear of unprotected people, vessels, vehicles or structures. The particular location is selected because it has a very open environment, which is perfect for many students to test their plane. However, the only obstacle is the flying surface that is made of tar. It could damage the plane when it barely lands or crashes if anything goes wrong in the flight test. For example, it would scrape off the surface of the plane, making it less efficient. The potholes present could also damage the plane severely. So now in terms of the marching paddock, the area has an approximate measurement of 200 meters times 100 meters by 100 meters, and it could sustain a large crowd. So since our class comprises of 39 students and 2 lecturers, there would be no problem in terms of overcrowding or flight test locations. Now moving on to the performing range check. The purpose of the range check is to make sure the radio signal from transmitter to receiver is strong, so that the RC airplane can be operated at a normal distance away without going out of radio range. This is very important because if the plane does go out of range, then all control will be lost, resulting in crashing of the plane. So what I have here is the meteorological check on site, and the graph here, the temperature. So this graph actually talks about the average temperature of the selected location, which is Johor Bahru. And so before that, the pilot should be mindful of complex wind profiles, as it can occur in all types of terrain. Carrying a handheld anemometer is suggested to check the wind conditions if they are within operational ranges. However, common sense would tell us whether the condition is suitable enough to conduct a flight test. Moving on to the next slide, which is the rainfall days. So this is a graph on the average rainfall days of the location selected. In theory, a model aircraft weighing less than 7 kg could be flown to any altitude, with the only limitation being the requirement to keep it in sight. We have decided to opt to fly our plane at an altitude of 10 meters so that it is clearly visible in sight and ensure it does not collide with anything, especially other aircraft. So flying site. Airspace of flying site is the flight area, or also known as box, inside of which all flying is to take place. For RC models up to approximately 72-inch wingspan, they'll be able to fly in a much smaller area. The flying site should consist of barrier, runway, safety line, pilot line or station, pilot pit area, spectator line, and safety equipments. So the first thing, which is barrier. Barriers designed to stop models from veering into pilot or spectators' positions. For example, they could be of plastic or chain link fencing. Second, which is runway. A runway should be designated within the overflight area of the site. This can be grass, dirt, geotextile, or hard surface. If space allows, it might be desirable to have two runways to be able to handle most of the wind directions. Next, safety line. So the safety line establishes the area in front of which all model flying must occur. Only personnel associated with flying the model aircraft are allowed at or in front of the safety line. This line can be straight, segmented, curved, or even box-shaped. Next is pilot line station. Pilot line station is where all pilots will stand while flying model aircraft. Pilot pit area is where pilots and other team stage and service their models. Spectator line is where spectators can view the action. It can be a simple line which separates them to a nice viewing area. And finally, the safety equipment. Safety equipments are the basic equipment such as first aid kit and fire extinguishers with appropriate ratings, and sand bucket for lithium polymer batteries. And the next slide, you can see our designed flying site based on the selected location. We have designed them where you can see the overflight area, runway, safety line, barrier, pilot line, and the pit, spectator, and parking area. So that is all from me. Thank you.